Hello and welcome. Today, school's in session. Now, this may not look like your normal classroom, and I probably don't look like your normal teacher. That's because neither are. I'm just a guy on the internet in my room. But I'd still like to learn you a thing or two. Now, kids, if a stranger ever tells you that, go find a trusted adult. Now, I want to take a look at carbon dioxide, going all the way back to the basics. It's actually a really interesting topic, and the science we use, it's beautiful. Though I am not myself a scientist, I am still in love with the field, and honestly, I'm grateful for any chance I get to get into the weeds with it. So, let's start. Carbon dioxide, chemically known as CO2, is a simple molecule made of one carbon atom and two oxygen atoms. It is fairly ubiquitous as it is a byproduct of most animals' respiration, or their breathing. This includes us. When we inhale, our body takes in the oxygen from the air, and our cells use it to produce ATP. This process creates carbon dioxide as a byproduct, which leaves our bodies when we exhale. What's fascinating is that nearly all plants use carbon dioxide during photosynthesis, combining it with water and the energy from sunlight to produce glucose. The byproduct? Oxygen. Plants do still need oxygen to break that glucose down into ATP, but they in net produce more oxygen. It's important, therefore, that we know how carbon dioxide works. While it is not vitally important to our lives in immediacy, it is a vital component to the entire biosphere of Earth. The entire project of life in the universe as we know it relies in no small part on this simple little molecule. It's an enthralling thought, and we have dedicated much time to understanding it. One very interesting detail that we have discovered about carbon dioxide and have been experimenting with since the mid-1800s is that it traps heat. Specifically, as we would come to learn later on, as our technology and understanding of light evolved, carbon dioxide absorbs infrared heat. Let's take a slight detour. Light travels as a wave, and as we all know, also behaves as a particle. Right now, light travels in waves, and these waves have specific wavelengths. What we see, what we know as light, is a small portion, with a wavelength between 380 and 700 nanometers. A nanometer is 1/1000th of a meter. For reference, a sheet of paper is 100,000 nanometers thick. Light exists at every frequency, but we can only see our very small portion. Light that is larger than 700 nanometers and out to a whopping, at this scale, millimeter wavelength is known as infrared. Just as our eyes take in light, so too can atoms or molecules. However, these particles tend to be incredibly picky about what light they absorb, being only of a specific small range of wavelengths due to various chemical and atomic properties. O2, a molecule of two oxygen atoms, which is how we find oxygen in the atmosphere, absorbs light at wavelengths of around 145 nanometers. Nitrogen, or N2 as we find it, absorbs around the 80 to 100 nanometer range. These are both ultraviolet. And we should be very thankful for this, as if they absorbed visible light, we wouldn't be able to see at all, ignoring the different evolutionary pressures that would have adopted us to let us see different wavelengths instead, but semantics. A little under half of the light the sun shines on us is in the visible spectrum. Yay, us! Also a little under half is in the infrared spectrum, and most of the remaining wavelengths are ultraviolet. Very little in the atmosphere absorbs visible light, so it comes to the surface, allows us to see, and then bounces right off the planet back out into space. To bring it back in, then, the visible spectrum of light travels to us largely unimpeded. Ultraviolet light is impeded significantly, as is infrared. To focus in on infrared, a lot of it gets absorbed while traveling through the atmosphere. This is then emitted again by whatever particle absorbed it, such as carbon dioxide. But this energy is radiated out in all directions. Some of it is sent down to the surface to complete its course, and some of it is ejected back into space without ever reaching us. Let's take another detour. What is heat? That's a tricky question with about 1,000 ways to answer it. What we need to know today is simple, albeit not perfectly accurate to the minutiae of thermodynamics. Heat is a measure of energy in a system. One of the main ways heat moves from system to system, or from one part of the system to another part, is by thermal radiation. Thermal radiation is energy transfer via electromagnetism, or light. When light, any light is absorbed by anything, energy is added to what it is absorbed by. When that something emits that light later on, it is radiating energy and thus heat. This is why sunlight, however little there is with the cloud cover right now, warms you, because the light itself creates heat. To go slightly more in depth, though not by much, heat can be measured as the thermal motion of subatomic particles, which is directly tied to the amount of energy that particle has. The more energy, the faster it is moving. When it emits radiation, it then moves slower. God loves billiards. Apply this, then, to the sun. It is constantly bathing us in light, which is energy, and thus heat. But we don't just keep this energy. We are always constantly emitting heat from our bodies as light. Everything on Earth is doing this. In the summer, as you near your car, you can feel its heat before you ever touch it. You can feel the heat of a sun-bathed rock by holding your hand over it. It is giving off heat. Similarly, I could hold my hand to a light bulb and I can very quickly regret it. This is the first law of thermodynamics. Energy is constant. What we receive has to go somewhere else also. The whole of the planet's surface is, at all times, remitting all the energy it receives back up into the atmosphere. This heat is in infrared. This is why infrared cameras are known to detect heat sources. Heat sources give off infrared light. This is not some special property of infrared, though it is easy to assume that given its ubiquity. Rather, the wavelengths of light is directly related to the energy of that light. When something is hot enough, like molten rock or the filament in a light bulb, it will give off light in the visible spectrum, but any normal temperature on Earth will be giving off heat through light in the infrared spectrum. This is a massive asymmetry. Just under 50% of the heat incoming to Earth gets absorbed and bounced around by carbon dioxide. Just under 100% of the heat outgoing from Earth is absorbed and bounced around by carbon dioxide. While it does inevitably send some of this energy into space, as was its path, a significant portion is still redirected into other parts of the atmosphere, or back down to the surface. The more heat that the atmosphere is able to absorb, hold, and keep within itself, the more heat that the overarching system of the Earth can hold at any given time. Therefore, the warmer it will be. In 1859, physicist John Tyndall, the same Tyndall that explained why the sky is blue unless you happen to live in Minnesota this week, forecast says cloudy for another 10 days, discovered carbon dioxide's infrared absorbing properties, and noted at the time that changes in atmospheric gas concentrations could contribute to a changing climate. These properties are easy to demonstrate even at home, provided you have a good way to measure infrared light. Examples are located in the description if you're curious. This property is the entire basis of one of the most common CO2 detectors, the non-dispersive infrared, or NDIR, however you want to say it, sensor. It emits infrared light at specific wavelengths and then detects the light that comes back to it. Depending on how much light is missing, it can measure the concentration of carbon dioxide in the air around it. These sensors, and others like it, are incredibly useful wherever carbon dioxide is important, such as in literal greenhouses, or where it is a dangerous byproduct, such as in many manufacturing or energy production facilities. You may even have one of these sensors in your home, or you may want to look into getting one for various reasons. Not sponsored, though I am interested if any carbon dioxide sensor manufacturer is viewing this. If it did not absorb these specific wavelengths, these sensors, of course, wouldn't work. Similarly, if it did not have these properties, none of us would be alive anyway to talk about this. No life would have been able to form on Earth. That CO2 can trap heat is what allows us to exist above freezing at any point in Earth's long history. Were some heat not retained in the atmosphere, the sun's energy would strike the surface and then later be radiated into space. None would be maintained to provide the general warming we enjoy, even if it is winter outside right now. We may imagine this hypothetical Earth similar to Mercury. It is by far the closest planet to the sun, and therefore when its surface faces the sun, the rock heats to 800 degrees Fahrenheit, or 430 degrees Celsius. And yet, due to its proximity and small size, the atmosphere of Mercury has been completely stripped away by the force of the sun. In the nighttime, temperatures drop as low as -290 degrees Fahrenheit, -180 Celsius. That, despite its proximity. Were our atmosphere unable to hold its heat, it would be as though we did not have one at all, and we would be an even colder Mercury. We've also discovered and played around with and rigorously studied and experimented with other fascinating properties of carbon dioxide. One of these is that, while not an acid itself, when dissolved in water it nevertheless reduces the pH of the water, and thereby makes the water more acidic. It does this through a very fascinating but simple process. When dissolved in water, some carbon dioxide molecules will combine with water molecules to form H2CO3, or carbonic acid. It is an acid because pH is a measure of whether a given substance releases hydrogen ions, which are single protons, or takes hydrogen ions. The former is acid and the latter is a base. Carbonic acid releases hydrogen ions and can also form into carbonate molecules and free hydrogen ions in a process known as dissociating. So the water becomes acidic. See, that pH is a measure of hydrogen ions is why acids and bases counteract each other, which is really cool. I never understood it properly until like 9th grade when I was taking senior chemistry, but that made it all click. It was always odd to me how seemingly unrelated substances just did that. But when they interact, they share the hydrogen ions readily, and then there's no more surplus of those ions, and then it's neutral again. God, chemistry is literally so cool. If you want to read more about pH, here's a good article somewhere around here, link in the description as well. There have been concerns over acid rain as a result of carbon dioxide pollution. These may be assuaged. Rainwater already tends to be slightly acidic, around 5.5 on the pH scale, which, keep in mind, is a logarithmic scale. It is true that increased concentrations of carbon dioxide will therefore dissolve more carbonic acid, but it would really never be sufficient to bring the acidity down to the requisite 4.4-4.2 pH range. Or not until we're all long dead from CO2 poisoning. Rather, acid rain is usually created through sulfur dioxide and various nitrous oxides, both common pollutants caused by heavy manufacturing and the general burning of fossil fuels, reacting alongside other atmospheric elements to form sulfuric and nitric acids. What is nevertheless important to understand about the danger of carbonic acid's capabilities is its impact on the ocean. The surface water pH of the ocean has been 8.2 for a long time, making it slightly basic. Carbon dioxide from the atmosphere has dissolved in the ocean for as long as both have existed, and that CO2 has similarly always formed carbonic acid. It is a delicate balance. How much carbon dioxide dissolves in the ocean at any given time is subject to a number of factors, just as any dissolvent is. In particular, three main variables are at play. Firstly, the particular chemical properties of the solute and the solvent, here being CO2 and water respectively. These are unchanging. Secondly, temperature. The higher the temperature, the lower the solubility of gases, or the measure of how much a given solute can be dissolved in a given solvent. As there is more energy within the solvent, it is easier for the gas solute to escape. Thirdly, there's pressure. Liquid and solid solutes are largely unaffected by changes in pressure, but gases, like carbon dioxide, are dependent on it. They follow Henry's law, which states that how much a gas will dissolve in a liquid is directly proportional to the pressure the gas exerts on the liquid. That is, the greater the amount of gas, the greater the amount that is able to dissolve. Gas will attempt to reach an equilibrium in pressure. If there is more dissolved than there is undissolved, then some gas will leave the solvent, and the inverse is true also. Think of opening this conveniently placed carbonated drink for the first time. Not sponsored by Crush Orange either, but again, if you're interested, so am I. Before it is opened, there is much higher pressure inside the container. But as you open it, and I'm going to struggle here with doing it one-handed or something, because I want you to hear this. Yeah, something like that. As you open it, the gas inside quickly equalizes with the atmosphere, which is lower, and so gas will continue to leave the solvent, hence why sodas go flat. If, for whatever reason, there was a greater amount of carbon dioxide in the atmosphere, the ocean would dissolve yet more of it, and it would become more acidic. We can, with this information, make predictions about the state of the planet and various components therein, and how they would change if the measured variable, here being carbon dioxide, were to change itself. That it is said to absorb infrared, we propose in our model that, throughout Earth's history, the concentration of carbon dioxide would causationally affect global temperatures. The higher the concentration, the higher the temperature, and vice versa. If we were able to plot this along a graph, we should expect, the ideal model states, near perfect correlation. Similarly, we would also expect to see a direct causational relationship between CO2 concentrations and oceanic acidity. This too, if we could plot it, would result in nearly identical lines across time. Of course, if carbon dioxide did not have these properties, we would not expect a strong level of correlation at all, and obviously we could not find any causational relationship. So, mapping out these changes across Earth's history will be the subject of Act 2. Class dismissed. You know, I had this in my room overnight for this bit, so it's kind of warm. So it's not the best, but I mean, it's still good. Still not sponsored, by the way. That can change.